So I'm continuing to work problems out of Chapter 7 from Taylor's Mechanics. And if you wouldn't mind, please liking the video and subscribing. I'm trying to grow my channel, so I really appreciate it. And I'll work more problems like this. So 7.16, we have a cylinder, and it rolls without slipping down an inclined plane, which is an angle theta from the horizontal. So first things first, I'm going to draw a little picture. They call this angle alpha. And it wants us to write down the Lagrangians and solve for the acceleration. And of course, the kinetic energy is going to be the rotational energy plus the translational kinetic energy. So no real problem there. And I guess we'll go ahead and start there. The kinetic energy is 1/2 mv squared plus 1/2 I omega squared. And if we just let this be essentially this slope be our x-axis, and we rewrite omega as v over r, then our kinetic energy then is going to be 1/2 m x dot squared plus 1/2 I x dot squared divided by, let me write this a little nicer, I x dot squared over 2 r squared. That's a little nicer. Okay. And then what we need to do is find the potential energy. So we have this cylinder here, and our potential energy is obviously the potential energy from gravity. So mgh, we'll call it minus mgh. Since it's going down, we'll let down be negative. The question is, what is h? Well, that's going to depend mostly on where it is here. So if this is here, this is your h, right? And h is equal to what? Well, it's going to be whatever distance is traveled here, call it x, times sine of alpha. So then your potential energy, in this case, your potential energy is just going to be minus mgx times sine alpha. And now we can construct our Lagrangian, which is just T minus U. Once you get the kinetic and potential energy, you're good to go. 1/2 m x dot squared plus I x dot squared over 2r squared plus mgx sine alpha. Okay. All right. This is good. So now what we want to do here is we need to solve for x double dot specifically. And the way that we're going to go about doing that is using our Lagrange equations of motion. So Euler-Lagrange tells us this. This is the Euler-Lagrangian, and this is kind of the equation we're working towards. On the one hand, if we take the derivative of our Lagrangian with respect to x, well, that's pretty easy. You just get mg sine alpha. And then we need to take the time derivative of the derivative of our Lagrangian with respect to x dot. So that's going to be mx dot plus I x dot over r squared. And then taking the time derivative of those two terms gives us, I'll just factor out the x double dot that comes from this, m plus I over r squared. Okay. And we can divide over to solve for x double dot, which is our acceleration. And this is your equation of motion. We have an expression for our acceleration. So not too hard, I don't think. Again, like with any problem with Lagrange mechanics, the first two things you want to do is write down your kinetic and potential energy. In this case, we had rotational and translational kinetic energy. This is a good little equation to have down in your formula sheet in case you forget. Potential energy, we had to think for a second about that, but we have that down. And then you can write down your Lagrangian. So write down your potential and kinetic energy, then write down your Lagrangian. And then use your Euler Lagrangian to get your equation of motion. Multiple equations of motion sometimes. In this case, we just had x, which is this big guy. Once you do this, you will get an equation with, in this case, x double dot, and we're going to solve for x double dot, our acceleration, which is what we did. So that's all there is. Hopefully that makes sense, and if it did, please like the video and subscribe. I'd greatly appreciate it. Thank you.